Okay, good morning everyone. Thank you for joining the tutorial this morning, either live or after the fact. So the subject this morning is scalable machine learning with a framework that I found a while ago and have used quite a bit called Ray. Let me start by introducing myself a bit. So my name is Steve Purves. My background is electrical engineering and sort of signal processing, computer vision. But I've worked in oil and gas industry for around 13 years, with mainly with seismic data, working with interpretation software to build interpretation software and to build post-act seismic analysis algorithms. After that, I've spent a lot of time working in different domains, building sort of full stack software. And over the last 4 years, I've sort of had my journey into modern ML. And during that, I've learned lots of things. And also sort of Ray is one of the things recently that I got into and I see making a huge impact. Not only when we're setting up sort of research and production infrastructure for machine learning, but it can have an impact to everything that you do with your models, even if you're working on a single machine. So I thought it was important to share that. It's a new library, and if more people know about it, more people start using it, I think we'll get a lot of advantage out of it. So we're going to start by setting up the repo and stuff in a minute, but just on the motivation front, today I'm going to be talking a lot about hyperparameter tuning, and hyperparameter tuning is the main focus of the Ray usage and all the examples that I have. And at some point recently in my ML journey, I sort of realized that model selection and the model selection process itself is critical, is involved, and that you have to tune your parameters no matter what. And often there's always many more hyperparameters that you have the time, money, or patience to try. And I'm sure there's lots of people out there with the same problem. And Ray helps us solve that by giving us a way to do that hyperparameter tuning efficiently and in a more scalable way. So just some housekeeping, as it were. You're on a live stream, but you can actually also pause the live stream. So at any point, you can just go and click and pause there if I'm going too fast or if I've already moved on. And I believe you can even back up a bit. And so I'm going to try and go slow. We've got 3 hours today, and I'm going to try not to rush through anything. But if I do move forward faster than you're going, just pause and keep going when you're ready. If you're on Slack, then please go and join the tutorial channel, T20 fri-ray. Dan Austin is in there and will also help out. He'll be listening for questions. Now, Dan's never used Ray or any of the tools that we use, but he is a sort of Pythonista and is familiar and sets up ML models and notebooks, so he can help out with a bunch of questions in general. If you do have questions about Ray and just questions to ask in general, if you just put those in there anyway, and we'll have a look at them during the break and answer them afterwards if we can. So the tutorial itself is based around a whole set of Jupyter notebooks that is set up in the repo I shared, but it was developed and tested on macOS and Ubuntu. I haven't run any of it on Windows, so that's a bit of an unknown factor. So if you're on Windows and trying to follow along by running code on your own, you may hit problems that I might not be able to help you with. But overall, I think if you just watch, even if you just watch the live stream, hear and see the notebooks getting executed, and come back to actually run those yourselves later, I think you'll still get a lot out of this tutorial. So don't worry. So let's get set up. I'm just gonna, let's stop sharing. I'm back. Okay, so let's just get set up, and we're gonna start by heading out to the repo. Now, hopefully you've already cloned the repository. The repository is up on GitHub at eClearity, which is me, and at Transform 2020 Ray. If you need to clone that, then I would just go to a dev folder on your machine, type git clone, do a copy there with HTTPS, and hit that, and that's going to clone that into a local directory for you. The repo is maybe around 150 megabyte, so it might take a little bit to download depending on your connection, but it's not too bad. Then, once that's cloned, you should see a layout like this. So we have a whole bunch of numbered directories that are the notebooks we're going to step through in sequence. We have a Conda environment file, and we have a datasets folder with a bunch of data. So mostly the setup is taken care of by Conda, but we will we actually need to go and do an extra step here. So in the README, in the repo, I've already included some instructions. And what we need to do is go back to sort of our development directory. And then just stay there. And then from there, first thing we need to do is install Node.js. Now, Ray comes with its own sort of dashboard that allows you to monitor processes and the tuning jobs, and that needs Node.js to work. In order to install that on Mac and on Linux, I have done the method with NVM. And if I just click on this link here, it takes you to the NVM page. And this is as simple as just grabbing this curl or wget, copying, pasting, and running that. I'm not going to do it because I already have a build set up, and that will install the Node version manager. Once that's complete, you're going to be able to run node command nvm, and you're going to see that you have nvm installed. Once you've done that, we can come back to the main repository. Sorry, come back to the main README. And we can also then install Node. Now we want to install Node with that version number. And if I come to NVM, I can ask NVM to list out what is currently installed. I already have the package installed. But if you don't and you just freshly set it up, you need to type NVM install v1440. Sorry, 1440. Hit that and it'll go off and it'll install Node for you on your local machine. Great. So Node.js will be on in the background and it'll be able to start the dashboard app. Step 2. Is to, now we're going to build the dashboard from source. To do that, we're going to do git clone for the ray project, like so. I've already got that checked out, but that's going to take just a few seconds to update. And then we're just going to execute the rest of the commands in order. So we do a push into ray, Python, ray, dashboard, client, which is just a fancy CD. We do an npm CI, which I've already done, so I'm not going to execute that. We do an npm run build, and then that'll build the dashboard. It might take a minute or so, and then we can just leave that running, and that'll build in the background. Okay, that last command was npm run build. So basically just execute those from the readme and you'll be fine. So while that's off running, and by the way, don't let any of this put you off, because if you don't have the dashboard, it's not the end of the world. So let's just go back, well, let's go back here, go to my dev directory, and go into my transform directory. Sorry. Okay. And now I'm back in my transform directory, the repo that I just cloned. Now the dashboard, like I say, it's optional. It's not the end of the world. If anything goes wrong in that install, don't worry. If it does, then just come back into your project repository and build the Conda environment here. So if you've just checked out the repo, I would then build the Conda environment from scratch. The Conda m create -f environment. And that's going to go, it's going to create a new environment called T20 fri-ray, and it's going to load all the package dependencies in there. I already have that environment locally. You may too, if you've already done this update, this step before. If you have, then I want to make sure that you've done a git pull and you have all the latest changes as of this morning, and then do a conda env update -f environment. And that's going to just look through the environment file, check any differences, and install any missing packages. Yeah? And that'll take a couple of minutes to run. So, yes, it's all solid environment. Okay. Good. I hope that wasn't too quick. Like I say, if the dashboard is an extra, if it is too much of a step or it's taking too long for you, just go ahead and build the Conda environment, and you'll be fine from there. You'll be able to watch me launch the dashboard. Cool. So you see, for me, the updates happened already. If you're doing a create, it'll take a bit longer. But afterwards, just activate your environment. Great. And then you're ready to run all the notebooks that we've got. Okay. So some gotchas. Now, I've set up the tutorials in such a way that you don't need a GPU to run this. You can just run this on a machine with no GPU, or with a GPU with a Conda, without Conda support, like a Mac. You may hit an error during install. If you do have a Mac or you don't have a GPU, and that'll be talking about this, the CUDA toolkit dependency. So I've just opened Visual Studio Code. Let me do that again. So from my project repository folder, I've just opened Visual Studio Code. And I've gone to the environment file. If you're having issues with this, just comment it out. And then rerun the install. I think this is because on a Mac, for example, or a non-CUDA GPU, Conda can't find the wheel for this, and it just doesn't install it because it doesn't exist for that platform. But so the workaround is just to comment that out. Cool. I'm going to comment it back in real quickly. Great. Cool. So just while people are working through those installs, I'm just going to say a couple of things. Like I say, we've been through the setup. If we can't get the dashboard built, it's not a big deal. At some points during the demo, I'm going to be using the dashboard to look at TensorBoard. Now, at those points in time, if you don't have it, remember TensorBoard is still installed. So at any point, you can just go into a terminal, run TensorBoard, and point it to the same folder as I'm using in the dashboard. And then TensorBoard is going to be available on port 6006 for you to look at. Cool. So just while those environments are getting set up, what am I aiming to do? Well, I want to introduce Ray in its packages. Ray is huge and it's developing quickly, so there's no way I'm going to cover all of the packages or even all of the aspects of the tune package. But I want to introduce it all to you. We're going to take a really close look at hyperparameter tuning using the Ray Tune library. And all of my examples are set up around hyperparameter tuning. And I'm going to do this through examples relevant to our domain as much as possible. That was, I think, one of the big things in this tutorial, that I wanted to try and bring in some relevant examples and leave you with some notebooks that executed those. And one of the big things I want to demonstrate is if we just have our code in the right shape in the first place, then moving to Ray Tune and scaling is actually very simple. The code changes are small. So as we go through the repo, we're going to have notebooks with a lot of code in them. But sometimes when we step from one notebook to another, there's only actually a few changes that we need to be aware of in order to use Ray or change our usage of Ray. And of course, I wanted to leave you with some notebooks as resources so that after this, you can start playing and then building out from them. I guess on the right is a sort of breakdown. I'm going to be talking about ML practices a bit, because that is sort of, I want to explain why we do this for people who aren't already doing a lot of parameter tuning. And then in there, I think we've got about 20% of the time with scikit-learn, 15 with PyTorch. And then, but around that, we're talking a lot about Ray Tune and Ray and Ray functionality, and we're going to be playing with that. And we've got some example data sets. We've got the breast cancer data set and the MNIST data set. This is mainly to be able to move quickly through the examples, but also if you don't have a GPU, you might consider just running those ones and not the main examples. And the design examples in our domain, I've got some litho Facies classification, and we're also going to do some classification on some fossil images. Those are much more compute-intensive tasks, and if you've got the machine available, you may be able to run some of those as we go. But if not, just watch along, and at the end you'll be able to play with this later. Okay. So, running order. Well, I think we've just done the first two steps. And we're going to move on after that to do some warm-up in scikit-learn. So I'm aware that maybe not everybody's familiar with scikit-learn or the bits of scikit-learn that I have been using. So we'll gently introduce those whilst talking about what is hyperparameter tuning and why we're doing it. Then we're going to do some stuff to get started with Ray, and that's going to be a combination of low-level Ray and Ray Tune. I'm going to try and launch and execute some things on an array cluster, and that's probably something that is going to be difficult to follow along on unless you already have your AWS environment and credentials set up. If you do, you probably know what that means. If you don't, then I wouldn't worry about it. It's not something I want to stop and help get people set up on. Then we're going to do some tuning for real on our well data for lithofacies. And then we're going to move into PyTorch and look at sort of deep trainables or trainables with neural networks, which in this case aren't that deep, but they could be if we had bigger examples. And hopefully we'll be able to get that through that this morning. We're going to take a break for 15 minutes in the middle. That's going to be somewhere around here, either before or after, depending on how fast we get through that and whether the cluster comes up and things like that. Okay, so let's get started. I will not stop the screen share this time. So here we are. I'm in Conda. I've done my Conda activate. So I am in my environment, and I have all my dependencies available. Now I've got multiple terminal windows open here. So let's make sure. Yeah, let's just kill this stupid notebook. Come on, yeah, good. Great. So I'm activated, I'm in my environment. Close that. And all I'm going to do to start off is type Jupyter notebook. Over here. And now I don't really need my terminal. So I'm just going to make this full screen. Okay. So where I want to start is getting warmed up. Right. So let's just take a step back from array a minute and then just think about training models. This will help us, introduce some of the patterns that we'll see repeatedly through the tutorial. And also we can ask some questions. So why do we tune hyperparameters? What is a hyperparameter? Why do I need so much compute then? If my model trains in 3 minutes, isn't that job done? And another thing that was something I learned over the last year was, what do you mean my validation score is a random variable in itself? So let's have a look at those things as we move forward. So most of my notebooks are already solved. So if you're just not going to run locally but are going to follow along, just step through the notebooks or just keep watching the live stream. If you are going to try and run locally, I would just go at the start of each notebook, like I am, and I'm going to restart and clear all the outputs. We should have cleared the outputs. Let me try that again. It's weird, usually. Okay, let's go with it. Right, so first up, no, sorry, I'm just going to try again because I really want that to be able to clear the outputs. And I've never seen that before. Okay, let's just try and run here. So first of all, I'm going to bring in my dependencies. And no, Jupyter isn't happy, I don't think. So let's just back up. I'm going to interrupt kernel. I am going to shut down this notebook server. Take a deep breath. I'm just going to have a look around a second to see. No, there's no other Jupyters running. So let's try that again. Cool. Am I ready? You start and clear output. Hey, sanity regimes. Okay, so let's get warmed up. So first couple of cells are just dependencies. We're bringing in NumPy and we want to do some plotting. So I'm bringing in Matplotlib and Seaborn. And then we're going to bring in a lot of stuff from scikit-learn. If you're a scikit-learn user, you'll see this. You'll recognize a lot of that. But we're bringing in data sets and metrics, and we're bringing in a train test split function to be able to split our data. Our pipeline itself will be built using make pipeline, and we're going to use a robust scaler for normalization and random forest. And we're bringing our metric, which is our F1 score. Now, the data set itself is a well-known data set. It's the breast cancer data set from the machine learning repository. This is bundled with scikit-learn. And basically, that's a binary classification problem that allows us, what we're aiming to do is detect whether, given a sample, the breast cancer is benign or malignant. So to do that, scikit-learn makes it very easy, of course. We just load the breast cancer data set direct from scikit-learn, and that gives us features and labels. So we see that the scikit-learn data set is giving us 30 different features. So we have 30 columns to our input vector. And if we just have a look at the outputs and just see how many examples fall into each case, we can see that there's a bit of a class imbalance between the two, with more malignant samples, but nothing extreme. Okay, so that's our data set. It's quite a simple data set. Next, we're going to define a training function. So this is, again, pretty standard. But instead of just writing the code out, we just make sure that we put it inside a function that's easily callable. That's one of the patterns we want to stick with if we want to be able to move to array. So our training function takes features and labels. We're doing a random split of the data set into train and test splits. And we're keeping the test size at 25% of our data set. We are then making a pipeline out of our robust scaler and our random forest. And now in this case, we're hard coding. So we're not doing any hyperparameter tuning. We've just decided these are our best parameters. We're freezing our random state. So random forest will behave the same every time. There's no randomness in there. And then we're fitting the pipeline. So that's doing our training. We're then predicting based on our test set, and then we're returning an F1 score. So great. And now we can run our model and get our score like so. It's all extremely fast. This nice small data set. So we can get a score of 95, F1 score, which is pretty good. But is that the best score? Or is that the only score? Or is that the right score? Because if I run it again, it changes. And in fact, let's run it 3 times. And we get different scores. But why is that? And immediately you might say, well, oh, there's randomness in there. But if you remember that our estimator is deterministic, there's no randomness in, we've frozen the random state. The randomness is actually coming from our split function. And it's coming from the fact that we have decided to draw a test split out of our data set and use that to measure the performance of our model. But of course, now our score is sensitive to that split. And if we do a different split, we do a different score. So how do we sensibly assess the performance of our model? Well, immediately you have to think, well, we should run this multiple times and see what the score behaves like. Once we do, say, 1,000 runs. So let's try that. So if we do 1,000 runs of that estimator and then plot the histogram, it's going to take a few seconds, we'll see what our actual score distribution is. And this is a big realization to make, that targeting these original scores, individual scores, isn't enough. We need to know what the distribution of those scores are, and that our score itself is a random variable that we need to estimate. So if we do it like this, we have to do 1,000 runs, but then we get a good sample, and we're able to plot out the distribution like that, which is slightly skewed, but it's still more or less centered around a central peak. And so if we squint a bit, we could say that's normal distribution-ish. So we're maybe happy to continue just modeling our scores as normal distributions and thinking about its mean and standard deviation. And that'll get us close. It'll definitely get us closer than, definitely get us something more reasonable than our single sample. So I think, and the statistician might correct me here, that something like this is called an out-of-bootstrap estimate of the model performance, because we're doing bootstrapping with replacement by continually resampling our test set. So if we do that and plot that a little differently, what this plot's doing is it's taking our 1,000 runs and it's plotting the distribution. This time we're modeling it as a normal, so we have a nice symmetrical distribution. And then I'm doing one more training run. And if I just completely keep running the cell, we can see this blue line jump around. And now we're seeing the red line is the mean. So that's the test score that we want to use. The width of this gives us the variance in our test score. And then these are our individual samples, which sometimes line up quite well with the mean, but sometimes they're off. So there's the first thing to think. Training an individual model and generating one score usually isn't enough. We need to do more runs than just one in order to properly estimate our model performance. And that means more compute. So even if you have simple models, we're already starting to think, but I need to maybe run these many times in order to properly estimate my model performance. So on to the second warm-up topic. This out-of-bootstrap method, if you go out reading the literature, has been shown that that is actually biased. There is bias in there. And that another method to use, is well known, in order to get a better estimate of that distribution, is to use k-fold CV, k-fold cross-validation. And that's when we sample a test set out of our training set using even splits like this without replacement. And I believe that's been shown that cross k-fold CV gets us a better estimate of our model performance than the out of bootstrap. And of course, it's much more efficient because I'm not having to do, say, 100 runs now. I can just do 5 folds or 10 folds and generate my estimate that way. So let's have a quick look at what that does to our training code. Let me clear the notebook. Okay. So we're bringing in some dependencies again, same as before, but now we're adding these two things in, and these are standard model selection things, modules from sklearn that allow us to do our k-fold validation. So we update our train function now. We've loaded our data set again. We upload our trains function now. And now the only real difference in here is that we now have a splitter, which is one of these functions from sklearn. And we're going to loop over each of those folds. And we're going to accumulate the scores. And then we're going to return the array of scores from the k-fold validation run. And I'll just run that to define the function. So now we're doing a k-fold validation run, and we're passing in just a k-fold splitter. We're saying it to do 10 folds, but we can play around with that. And we're telling it to shuffle, because by default, they won't. So they're shuffling, and so there's some randomness in the k-fold still. And let's just run that. And now immediately we get out our distribution. We can see an F1 score centered on 9.7, and with this standard deviation. Because we're shuffling, we can run this multiple times, and those numbers will change. But what you find is those numbers don't change as much as we've seen before. Well, that one's changed quite a lot, hasn't it? Let's reduce the number of splits, which means our test set is bigger. And then maybe set's a bit more stable. But then that gives us a more efficient way to do it. So now we've run that twice, and because of the randomness, we still get different numbers, but we're going to see that those distributions overlap quite well. At least their means are quite aligned. So this is generally a better way to do it. But again, you need to do multiple model runs. You need to do this k-fold over potentially a large number of folds, depending on your problem. Okay, and doing this, even though we're not parameter tuning at the moment, doing this is essential in your parameter tuning. So, next up is now to start doing some parameter tuning. And now we're going to take sort of the simplest possible approach to hyperparameter tuning is grid search. Because let's face it, everybody loves to exhaustively search 10D multi-parameter space. And that is something which definitely starts to ramp up your computation. Because imagine even a one-dimensional parameter space. Imagine we want to test 10 different variations of a parameter, each of those running cross-validation. So we can see that, well, say 5-fold. So immediately there's 50 model runs in place of our one model run before. But maybe getting ahead of myself a little bit. Let's just come in here and clear up the notebook. Let's run our first two cells. And again, this is the same dependencies as before, but now I'm just bringing in this grid search CV function, which is a nice helper from the sklearn module selection module again, which is going to save us from writing a lot of code. And now I've changed our train function, and I've called it tune, because we're tuning rather than training now. And our function takes data the same as before. Well, I think I've renamed it to X and Y now, just to be more compact. But it also takes a parameter grid, which is the space over which we want to do our search. And it also takes a cross-validation strategy, which can be none, in which case it'll just do individual rounds. And it'll also take an end jobs because actually scikit-learn can already do some parallelization. So that helps you speed up if you need to. Well, it helps you to speed up just out of the box. You can run multi-threaded. Same as before. My pipeline's there, except I've not parameterized it now. When I did it, so there's no default. I'm just going with whatever the default parameters are in there, and that's because grid search CV is going to inject the parameters on every single run. It's going to manage the search for us. So the grid search CV function takes a pipeline, takes a parameter grid. I tell it how I want to score, and I'm just using the F1 micro averaged again. But you can do anything in here. You can actually inject your own functions and get pretty fancy about how you evaluate the model. And then we're going to inject the CV, and we're going to tell it, we're just going to pass in the cross-validator and the number of jobs. We run search fit, and then grid search actually returns a big data structure that we can pass that has all sorts of information for us. So just as a note, previously, we were using a model with 15 estimators, entropy, max features, auto, bootstrap 2. So that's just a reminder there of what the original parameters were. So let's go off and search. And that was pretty fast. So, because we've got a small data set. So what I did there was we defined a parameter grid. Now, we've got this huge long name here because it's, as it so happens, if you build a pipeline in scikit-learn, you can inject parameters into the fit function or into here that will take on the form of pipeline step, double underscore, parameter. So it's good to stick with that pattern because you get a lot for free. And so here we've defined a parameter grid, which is one-dimensional, and we're searching over num estimators from 1 stepping up to 100 max. We call our tune function, and then I just define some functions that we're going to reuse below just to print some facts out. So that took 1.2 seconds. The best index was 4, and it was the one with the most estimators. And then we got an F1 score of that. Now, if we plot all of the results for the different estimators, we see we got all these different distributions. So our best one was 100 there, and there's our score of 0.56. But they're all pretty wide distributions. I have to watch out though. Look at the scale here. We're only going up from 8.5 to 0. So they are still up at the top end of the scale. But this is good. We can see what the mean was and also how much variation there was over the different folds within our test set. The tighter the distribution, the better. Cool. So that was quick, 1 second. Let's up the compute a bit more. So now we got a 3D search space, I believe 150 calls to fit. And we're going to go across the same estimators. We're going to flip between these two different assessment measurement criteria, the Gini and the entropy, and we're going to try with and without bootstrapping. This is going to generate a lot of models, though. Too many to plot. So I just wrote this little function here, which we can ignore, but that just takes the n best for the purposes of plotting. So our best result in this place was, that's not very nice. This is from pprint, import pprint. Yeah. So the best one was with no bootstrap, with entropy and with 100 estimators. And if we do some plotting there, we now see the different results. Some interesting things going on. We have a better mean score here with a slightly wider distribution. So we've increased the score a bit from our last run by searching over multiple dimensions. Sorry about the legend here. It's not showing all parameters, but you would be able to mine the results again. Now, how long did that take? That took 2 seconds on this machine. And I'm running with, I believe, sorry about scrolling down, 10 jobs. Let's really increase the size of the search space. See what happens. That might take 20 seconds or so. But let's see, we may get another job out of it. We may get another best score out of it. So basically, that's hyperparameter tuning. We do it because we want to try and find the best model that we can, a robust model which is scoring well and remains stable over the cross-validation output. But grid search is not great to do on a big on high dimensional spaces. We've got here, this one took 40 seconds, where the last one took 2. So that's a factor of 20 scale up. And even though that's quite quick for our small model, we haven't, even that's quite quick for our small model, we haven't actually, no, sorry, it's still quite a significant scale up if we had a more complex model. And again, we have a whole bunch of scores to then go and choose from. Not quite as good as the last one. So grid search is okay, but is there a better way? There is a better way. And when you're dealing with actually wanting to go out over many parameters and tune over many parameters, it's often good to do a randomized search strategy. And then once you know a ballpark, then you can maybe go and refine and fine tune with grid search. So just to visit this quickly, the scikit-learn model selection also gives us a randomized search CD. And I just want to go through this quickly because we're going to see the same patterns in arrays. So now we have a tune function again, pretty much the same inputs, same pipeline, and we are just returning what the grid search returns. Now, this is the interesting bit in terms of what happens when we go in and set up a parameter grid. It's no longer a parameter grid. Now we have a parameter distribution. So what we do, our choice, our discrete options just stay as arrays, and that will be sampled from. But then whenever we have another sort of continuous quantity, we actually provide a random generator. So we actually provide a random distribution over which the grid search can sample for us. This means we're going to get much more finer grained samples. For example, on n estimators, we're not just going to get 1, 5, 10, 15. We're going to be able to get any intel over that range. And the random search module is going to manage that for us. So here, I've asked it to do 100 iterations, again, using 10 threads. It's doing stratified k-fold CV this time with 5 splits. And we've got similar results. So, and that took 10 seconds. So we have a different strategy now in order to target and do some hyperparameter tuning. And when our search spaces get large, we can use randomize to go and target those spaces, figure out which groups of parameters are the most interesting, and then maybe grid search. Okay, so I think the takeaways from that is basically we've seen some patterns. We know we should be doing cross-validation of some type, and we have looked at a couple of search strategies. They're not the only search strategies. There are actually many different search strategies out there that are used to tune models, and we'll see more in Ray. But we're already starting to see, even with a very simple problem, how quickly this compute scales up. And that's why we need a framework like Ray in order to train. In order to train things. Okay, so we'll move on to the next thing. These two tabs have crashed. So I am just going to shut them down. That worked. Okay, cool. I'm going to move on to the next section. I'm going to restart my notebook server. That's very strange. Maybe it's a product of having Zoom open. Anyway, restarting can't hurt. Cool. So now it's time to sort of get started with Ray. And let's go through this section next. Okay, so Ray is not actually at version 1 yet. It's growing fast. It was developed by the university, the RISE lab at the UC Berkeley. And I think since they've spun it out, and now there's a commercial organization, Anyscale, pushing the development and providing support. So I think we're going to see some big things because of that. The documentation of Ray is really good. It's big, but it is comprehensive. And apart from what I'm going to cover today, if you go into some of the tutorials and the guides, there's some Colab exercises in there already. You can go in and there's lots of examples. Lots of tutorials to work through, either in Colab or in Jupyter. So that's definitely something to go and explore afterwards. But here we're just going to look at one way of using Ray with some domain-specific examples. So let's get started. So I've got Ray installed on the machine. I'm going to load dependencies, which is basically those top blocks from the last few notebooks. I don't want to keep looking at those. And then I want to import Ray itself. Now, Ray is the main module that we bring in, and that's responsible for managing the jobs and running the clusters and stuff. And to get things started, all we have to do is say Ray init. And that will have started up in the background a cluster for us. Now I say cluster in this sense, we're in a local machine. So cluster in this sense means multi-process cluster running on this machine. And now I'll go into the Ray dashboard. Ray handily prints it out there in a little message. And if you've got the dashboard, then you get the benefit of this. You can actually see what's going on the workers. So here's our main machine here. And it's got 16 cores on this machine. And Ray, by default, has consumed them all and set up a worker ready to run on each. So if I run now, probably I'm going to have troubles with Zoom. Definitely. Oh. Come on. In fact, I'm already having troubles. I don't know if it's this overlay from Zoom. I don't know. So I'm going to actually shut that down. Okay, if I call a shutdown, go back, the dashboard's not there anymore. So I'm going to run ray-init now, and I'm just going to tell it to not use all my threads. I'm just going to tell it to use num CPUs equal 10. It's actually up the port address there, so let's just do that. Okay, now we have 10 workers set up, ready to run. So this Ray dashboard is still in development. This machine view is useful because it lets you see what's happening with your resources. The logical view, I've not used that yet, and tune doesn't trigger it, neither the Ray config. This is more for when you're working on the cluster. But the tune tab here, which again is experimental, but that is what it allows us to look at the tune jobs once they're running. Yeah, that's definitely to do with the Zoom. There we go. Okay. So let's go back here. And actually, I'm going to be brave and just pull that out to a separate area so we can see these side by side. Okay. Right, so the Ray cluster up with 10 CPUs. So Ray itself is an extremely powerful distributed computing engine, and you don't have to use it with any of the ML stuff. You could just go out and use it as a basis to distribute any code, including plain Python functions. So here I've got a very little function that is just going to loop and increment a counter, and then it's going to return the square root of it. And it's decorated with this array remote decorator. So we just define that. And then I'm going to run. And then you might have seen a tiny blip there. And what that's done is it's pushed this function out to all workers. It's run it. And then it's pulled back the result via these futures. So as soon as the job runs, you get a future or promise token back in your main thread. And then that will be populated with the data once the job completes. And you can see here, I got all those results back. From 400 remote invocations across those threads. If I add some zeros here, just to use some electricity, it's still far too fast. But now we can see the cluster blipping a little bit. So you're able to go and invoke things on the cluster. And this could be the local cluster here. So you've got really fast multiprocessing immediately. This could be the local cluster here. This could be a cluster on the cloud. It could be a stack cluster. The Ray allows us to abstract between all these things with the same code. So I'm going to shut down an init again. And num CPUs, again, equal to 10. Cool. And let's pop that back over here. Okay, so we've just reinitialized things. And this is just to show you a slightly different pattern. So again, Ray remote decorator, but we're now assigning that to a class. So we don't just have to pass out a function to execute. We can send an object, which means it can be stateful. So that means this thing can keep a count, increment itself, etc. And these are just silly examples from the docs, but it's interesting to see that. And that blipped again. We could do something more fancy in here to make it run for longer, and we'd see that. But it's the same sort of pattern. We launch 20 or 200 if we want. Oh. I shouldn't have done that. Because it's launching threads. Shut it down. Before my computer dies. Good. Let's just rewind. It's the same thing. What's interesting about the pattern now is when you've got the object, you can actually interact with the whole object interface with remote calls. And the same way, you can read back then also the state of the object as well, and concatenate it. So you have this sort of pattern where if one process is my head node, you can distribute, suck things back to your head node to actually then, compute something on the partial calculations or whatever you've accumulated. Cool. I'm going to shut Ray down. So it's as simple as that. And that sort of simplicity, and I guess there's a lot more to it. There's a lot more Ray can do. But fundamentally, that framework is what is lying behind a hyperparameter tuning, this ability for Ray just to send jobs out on the cluster. So let's see now what our scikit-learn examples look like with grid search. And we're just going to go through this quickly. So let me clear the output. We're going to load all those dependencies that we've already seen. We're going to bring in Ray, and this time we're going to import the tune library. We're going to start Ray again on refresh. Yeah, that's live. We started Ray again with 10 CPUs. And now we're going to set up some Ray tune compatible training code. And now actually we were very close to this already because we've been working with these train and tune functions. The main difference is we want to make it now end to end. So the function that we sent to Ray or tune isn't only responsible for just doing the tuning, it's also responsible for getting the data, computing all the metrics and stuff. So, if you're in a notebook working on your own, this is maybe the pattern you wouldn't do because you would say, well, why do I have to keep reloading my data set while I'm going around this loop? But if you just do that, move that inside your function so it becomes end to end, then you're able to run this on Ray. So here's our end-to-end simple training function. We're loading the breast cancer data set. We're setting up a CV strategy. Just like you've seen before, we're iterating over the splits, doing our training, and we're accumulating all the scores from our CV folds, computing the mean and the standard deviation, just as before, but instead of that being spread out over the notebook, we've compacted that into this end-to-end function. Great, that's step one. Previously, we had a parameter grid that looked like this, where we're sending this into we're sending these things which are pipeline step parameter straight into the scikit-learn stuff. And these are plain arrays. What we do this time, though, is we convert this to be able to use tunes distributions. And we're doing grid search. So all we do is we wrap our array in a tune grid search object. And then we have a tuning config. We call a function called tune run with our end-to-end training function. We pass in our tuning config, and then we could leave it there. But what I also like to do is specify the number of resources per trial. So back up in our init call, we'd sold Ray, we've got 10 CPUs available. Here, we tell Ray, this training function needs 1 CPU. And like that, we can adapt. We can specify the training needs that we have. If we need a GPU, we would just increment this to 1. If we need 4 CPUs, we'd do that. And then that lets Ray manage about how many concurrent runs it can manage while it's running the job. And then we specify our local directory. By default, it goes into Ray results in your home directory, and I just put subfolders in so we can separate things out. And then we run this and we get that. So what we get is we get some summary for Ray. We get a list of pending jobs. And then Ray starts going and crunching through them. So we get, this is a lot of output for a Jupyter window. But this happens really fast in our example. We have everything trained and the statuses are terminated. And our tuning job is done. If we go back up to this run function, sorry for scrolling around. Actually, a good thing to do if you're running this is just hit that thing in the side so this becomes scrollable. If we come back to the function, you notice here from tune run, we returned an analysis object. So what Ray does is it builds this analysis object, and we can dump a data frame out with that. And that data frame is then available for us to go and analyze. There's lots of information. We've got the scores in that was achieved. We have all the information on the hyperparameters that we used, where to find any saved results, etc. So we can get the best config, which again was 100 estimators, out of that analysis object. And we can also go in and, plot results again. And the same way we can now go and look at the distributions of those training scores. Cool. So let's really, I'm not going to go for the full 6D run. Let's just try to start with 3. Everything's the same. Let's run the analysis. So that's all pending. Go at the dashboard. We should see things pick up. It was too fast. So let's run all those and terminated them all. And now we've got our best parameters. And we can produce the best results. And we've increased a little bit our score there. But there's some randomness in our draws, remember. To take that out, we might want to be deterministic and set the random seed of our k-fold as well. But we probably do want to do that, actually. But anyway, we're able to visualize our scores, and we have it in that data frame, so we could go in and do more analysis. So I'm just going to, let me add in another dimension here. And see if that's still pretty fast, not really showing up. But anyway, we know what's happening because do I have the right dashboard? Yes, I do. Okay. Anyway, it's done. And it must have done the compute because we have answers. Oops, sorry. Yeah. So the mean is one score. Yeah, and things have moved around. Cool. So the other thing about Ray is that also logs to TensorBoard. So if I go out here and in my home directory, go to Ray results. Here's a whole bunch of runs. I've just run the grid search, simple training. So it gives you this folders of all the different runs, and this has got TensorBoard files in there. So we can load a TensorBoard extension, and we can bring up TensorBoard and have a look at the results. Obviously, this is just a one-off training. It's not iterative training, so it's not, we don't get curves or anything. But TensorBoard is still interesting because you can come in here. It integrates with the hyperparameters module. So you can come in here and look at those. The metrics that I chose are the mean and the standard deviation of the F1 scores from our cross-validation. Ray puts a whole bunch of other things on, like time steps, etc., and iterations. but I'm going to take that off. And if we do, we can go over to parallel view. This window's a bit tight. And then you can actually start to see where some of those mean scores came from, and use the H-params module for that. It also gives you the scatter plot view, so you could go in and look at what's happening in there. So we can have a look at really where are the highest and one's sitting. Anyway, you have the full power of TensorBoard available for doing that sort of thing. Cool. Well, let me shut down Ray. Great. So we just moved out of sklearn world into Ray, distributed that compute over multiple processes with what was actually very little code change. So it's very easy to do that. We'll just quickly look at random search. Again, I'm using, let's go back to using 10 CPUs because that's what we're using. That's been working okay. And now we're going to do random. So I've actually moved all the functions and stuff into a separate file, and we've loaded those because we don't want to see all that. Basically, you want to go back and just think about, well, what's different when we're doing a random search? And with Ray, it's actually all about just how you define the parameter space. So previously, we defined our grid search here using the grid search function from Tune. And we can replace grid search with a bunch of things that Ray gives us from its random distributions API. So here we have log uniform, choices. We can build our own with sample 2. We can get random ints. Or, well, yeah, just random. Is random n random ints or random normally distributed? I can't remember. But we can sample from all of those. And moving into a random search is just about changing out those grid searches for the distributions. And when we do that, we need to make a slight change to how we call Ray, because we're not grid searching anymore. When we grid search, we know how many iterations we need to traverse the grid. Here we're random sampling, so we ask it, we tell it to do a certain number of samples. Let me do 50, for example. And then that will set up and invoke 50 runs in the search space. If we put the bottom here, if it goes, I'm not trying to chase that. Let me go back up and pop over to the dashboard, which is now 6. I missed it again, it's already finished. This is the thing with dealing with these small problems. They're fast to run, but they're already solved. So, okay, it went off and did that. And then as before, we can query the analysis to get the best results. We've got a whole data frame available, so we can get the n largest. And we have our tuning scores out, so we're in a position now to select a model. And again, we have that available in TensorBoard. So the key point there was just to show that change to the search space, the structure of the params grid, as it were, and just using the right functions to define our search space has enabled us to use a different mode of operation. Cool. 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 Right. So, before the break, as we will have a break soon, maybe now or maybe in another 15 minutes, but I'd like to show you what, obviously everything that we've had here is on a local machine. I'd like to show you what Ray helps you with in terms of getting a cluster, a real cluster set up. This isn't something I've done a lot before the tutorial, so it's something I've been working on over the last couple of weeks, and let's hope it goes all right. And basically, the Ray Autoscaling, well, let's step back a bit. Okay. So basically, the whole premise of Ray is to be able to go out and carry out distributed experiments. And there's a variety of ways to set that up. If you already have a cluster out there somewhere on your network or your institutional company network, you can definitely go and align to that cluster, connect to that cluster, and submit jobs, etc. You can set up that local cluster manually, you see, by specifying what the names of the IPs are, etc. You can manually set up a cluster, or you can do something which I'm going to do now, which is to launch a cloud cluster. So out of the box, Ray automatically supports AWS and Google Cloud. So that means from the Ray interface, we can go and bring infrastructure up, send jobs to it, and bring it down. And that's what we're going to do just now. Okay. So first of all, this part of the tutorial, you're going to be able to do if you've got your AWS credentials already set up. I'm not going to go through that now with anybody because it involves, dealing with secrets, IDs and stuff. But a way to test whether that's set up already is if you just run this cell in this notebook. This loads up the Boto 2.3, which is a Python module for talking to AWS. And it's just checking that you can create a session. And in this case, we're just listing out all the S3 buckets on this account. There are none, but we get an HTTP status code of 200. So we're all set up to talk to AWS. Cool. So in order to do this, I'm just going to switch over here. Cool. And I've got another workspace set up. So here I am in AWS, and let me refresh the page. It hasn't kicked me out. Good. And I'm in North Virginia, which is that's the US East 1 region. Okay. I'm in my getting started with Ray folder. And I've got two YAML files there, cluster minimal and cluster tune. We're going to look at cluster minimal first. So I'm going to open Visual Studio Code, do cluster minimal. And this is just something taken from some of the Ray docs. So Ray works by, you define a configuration, an infrastructure configuration in a YAML file, and then that becomes the reference point for your cluster. As long as you have that YAML file, you can invoke commands and work with that cluster. This one's pretty simple. They can get extremely complicated, but let's just have a go with this one to start with, just to see what that's like. Basically, a unique identifier. So a cluster name list, for example, minimal. The maximum number of workers to launch in addition to the head node. So when we launch a cluster, sorry for a second, there is a picture. Aha. When we launch a cluster, here, I'm on my local machine. There will be a head node created, and then that head node will be responsible for marshalling of all jobs and running the worker nodes. Yeah, and then we'll communicate via Ray from our local machine. So we're specifying that there are 4 workers in addition to the head node, that we're working with AWS, and it'll automatically find our credentials in this region. And we're working with the Ubuntu instances. So we're going to start up a head node, which is a C5 2x large with the latest deep learning AMI, even though we don't really need it here. But anyway, the latest deep learning AMI. And our worker nodes are going to be C5 2x larges too, with the same thing. So let's go ahead and do that. And just so I don't issue the wrong command. Okay, that's fine. Because I just need to read this. We just do this. So so ray up, cluster minimal. Yes, we want to create a new cluster. Cool. I just want to, I'm not going to sit and watch it cook or anything. I'm trying to move this zoom thing. The zoom thing is just in the wrong place. Oh, I'll just refresh the whole page. Okay, so there's a head node coming up. And Ray is sort of off doing its thing. Let's give this another 10 seconds. These apparently are normal messages. Cool. I tell you what, we're going to come back to that, I think. And we can do 2 things now. We can either, okay. Let's use this time while this is getting set up. So this is our minimal example that we're just going to try and publish a job on. But I've also set up a larger cluster that is already running over here in Ohio. So these are exactly the same machines. I think the workers are C4s. But the head node's running there, ready to be used. And that's had a bit of additional configuration. So that's been set up so that we can run some of our notebooks actually on that cluster. And let's pop back to Visual Studio Code and see what that cluster tune is like. So this other cluster, the config file is a bit larger because I'm doing more setup. It's called Ray Tune. It can spawn up to 8 workers. It's in a different region. The head nodes are pretty much the same. I just gave them more space. The workers are the same. And it's done a couple of different things. These are all different options. So file mounts. So when I brought that cluster up, it automatically took up all the code from my local directory onto the cluster. So we've got the full repository up there. It also ran setup commands and installed the dashboard, installed Anaconda, installed Ray. And basically in here, you do all your base setup commands. And then you can go off and do additional commands to set up your head, set up the workers, which I think if you were doing this in a production way, you would do that. But for the purpose of the tutorial, I basically brought the cluster up and then did some manual changes to allow us to run notebooks. So that second cluster is there, and the examples in the folder. And we will go and look at that after the break. But we'll go back at the moment to this minimal example. So that was up. We now have a worker. We have a head node. And now to access the head node, we can just do Ray attach. And again, just do cluster minimal. And then immediately we've got an SSH session on there. Yeah, so immediately we can go in, we can execute jobs, etc. If you like, if you need to do that or want to work that way. But what you can also do is actually submit a job directly from here. Now imagine again, if we're in a production sense, I would have taken our scikit-learning random search, maybe pushed that out to a different repository so that I could invoke a command and it would bring the code onto the server, run our training job, and bring back the scores and the hyperparameters for us. But in this case, I've just defined a very simple script called tune script. And that just does our example that we saw in the notebook of a simple ray function. This time I'm burning a few more cycles. And we can just now submit that job to the cluster. It's the wrong command. It's a cluster minimal. And it's off doing stuff. So what we should see is this thing spinning up worker nodes. There's one. Depending on this may be more or less exciting depending on your background and inclination, but I love being able to just sort of bring up infrastructure like this without having to do the points and clicks. It started one node, so maybe we didn't give it enough. Our job was too modest for it to start up to the 4 that it can. But that's going to go off. It's going to initialize, which obviously takes some time, and then it will come execute our remote task and then return back. Cool. So we're not going to wait on that. I'm going to now flip over to our next section, which is about tuning little Facies models from the 2016 Facies contest. And we're going to do that here locally, and then we're also going to try and then go and do that on the cluster that I will set up. However, we are going to take a break because we need a breather. So please come back for that in, I would say, 12 minutes time. So that'll be at 10:40. Yes, at 10:40 British Standard Time, which is maybe 9:40 UTC, but don't quote me on that. Okay. Thank you, Rob. Hi there, and welcome back. Great, so I hope you had a chance to stand up, stretch your legs a bit there, get moving again. So I think we're about halfway through, so I think we're doing okay at the time. Before the break, we did a couple of things before the break. So one of the things we did was, of course, we started up this little minimal cluster and sent out a job to it. When we sent out the job, it fired out one worker. It could have fired 8. Probably the job that we sent it wasn't big enough, but it completed. Yeah, in our little function example, came back with all the numbers that it had counted over those 400 threads. I guess it's because these instances have something like 96 CPUs on them, so it wasn't much of a task for one. But that showed the pattern, showed that we can bring clusters up, send jobs to them, and very simply from a command line interface and a YAML config file. So what I'm going to do is I'm going to bring that back down now, so that we're not giving Amazon any more pennies. And it's as simple as that to bring back down the cluster. Cool. And if I refresh here, because the zoom widget's in the way of the other one, you can see that, yeah, it's stopping everything. Okay, so that was a toy example, but just to give you a flavor of what that low-level array is like. And now we're going to move on to looking at a more challenging task, something that requires a bit more compute and one that is in our domain. I wanted to put this together because it is in domain, but as well, the notebooks here are available for people to play around and maybe, do a bit more work or continue some of the work on that Facies competition data set that sort of Matt at Agile and Brendan put together back in 2016. So I decided to pick up on that. So if you're not aware of this, there's a repo out there on GitHub, just SEG, not Segway, force of habit. SEG 2006 Facies contest, I think, will get you to the repo with all the data, all the results in there. It was fantastic competition. The idea was that given a set of wireline logs and a Facies target, could you make a prediction of the Facies in there? Matt and Brendan held back 2 blind wells completely from the package, and then they were used at the end to actually score and maintain the leaderboard. At the end, the top 4 teams there are highlighted. The winning team, which was Lucas Mosa and Alessandro de la Fuente, LA team, they uses boosted trees algorithm, which they tuned in Teapot, I think, or did AutoML style selection using Teapot. And boosted trees were pretty prominent at the top of the leaderboard anyway. So what I've done is I went and took their notebook. I ran the pre-processing scripts that did some imputation of missing log data and computed the features. And then I splattered that all out to what do you call it? A NumPy file. So if we go off here and look at our datasets folder, there's a folder called seg 26 Facies, and there's an H5py file in here, which contains the labels and Lucas and Alfredo's processed features. So everything you need to go straight into the model. And then what we're going to do is we're going to set up a random forest again, but now we're going to use tune to train it and see how far we get. One thing I have to say though, what I haven't done is integrated the test code yet. So there is some code on the official repo that allows you to compute the actual test scores that were here in the data set. Sorry, we're here in the leaderboard. And I just haven't had time to do that. That's something I want to do after the tutorial. We'll probably update the repo with the script allowing you to calculate these should you go off and tune and try and beat those scores. But at the minute we're going to be looking, so in this notebook we're going to be looking at the scores from the k-fold cross-validation, which are lower than the test scores and are expected to be. So just because our scores are lower here doesn't mean we wouldn't rank on the leaderboard at all. We could, but we'll have to leave that for later. So to get started, we're loading up some dependencies. We're grabbing the data in that H5Py file, which I've just organized in a bunch of different data sets. So we've got the train X and the train Y data, which is actually all of the data that was available to people in the competition. We've got the groups, which is essentially well IDs, and we've got the well names. We've also got here data called test X, pardon me, which is actually the blind wells that we used for scoring. So that's loaded here and is available, those features, but we're not actually using those in training or validation. We're going to do cross-validation over this data set. Okay. So the tuned model parameters from the winning submission I've listed here for the XGBoost classifier, just for reference. Let's load the data set and define a tuning function. Now, we'll recognize this from before. It's very similar, except now we're calling our setup function to get our data out of H5Py. We're defining a splitter again, but we're doing something different this time. We're using the leave p groups out splitter. So our groups here are our well IDs. So what we're actually doing is we're leaving an entire well out of each CV fold and using that to validate against. And then we're doing that round robin. I think Lucas and Alfredo might have actually had this set to 2 during their training. I'm not sure, but I've set it to 1 anyway. That's something to play with. And here we have so then we have a training loop. We accumulate scores. We loop over the splits our splitter gives us. We have a pipeline with a robust scalar and XGB classifier. And I've just realized I should probably be setting the random seed. And I'm not, but I'm not going to go and look at docs right now for that. Or shall I? Okay, I'm not going to. Let's just live with that for the moment. I'll research that later. So we make a pipeline, we set the parameters, we fit as usual, and we go ahead and predict. And then we accumulate our scores. Okay. The winning submission as well. Actually, I think there was some sort of medium filtering operation to take out isolated Facies from the results. I put this code in here, but it's not being used in the score at the moment. That's something that can be played around with too. And then we're going to call tune track to log our mean and standard deviation from our scores. So we have a tuning config. Yeah, thank you, Lucas. Optimize over random seed. Yeah, I know. So the tuning config. Right, so what we have to do is we have to move our tune config into here. Aha, this is what I've done. We're not optimizing over the random seed, we're fixing it. But we're fixing it in a way that it gets injected into the sklearn pipeline and is set as a constant on every iteration. Good, I had thought about that, I'm relieved. But the rest of these things are given a distribution. So we're going to be sampling from a log normal from our learning rate, a random int for our max depths. And we're going to be picking from choices for the core sample by tree weight. Okay, so let's do that. Let's set up our cluster. Oh, let's shut down an init array. See if the dashboard wants to play this time. Okay, I didn't want that to pop into a separate tab. But yeah, 12 workers for some reason. I guess that's demo day stuff. And then let's run the analysis. Let's just do a very quick sort of smoke test. Over 3. Yeah, it's running. It's terminated already. And we can see already, if we put a realistic task now, and the compute is much more significant. And some of these XGD boost runs you can see are much more intensive than others. Cool. So that worked. So let's go for a few more runs. Leave this to run for a few seconds. And do all that. And let's put TensorBoard on. Cool. So let's let that run. While that's running, I want to show you something else. So we've got this log dir here. TensorBoard in the notebook's okay, but it's really cramped. And even if you increase height, it doesn't do well with the H params. So what we can do here, yes, look, we've got all these 10 workers crunching. We must have a couple of orphans from somewhere. Pardon me, up there. But basically, we can come over to the Tune tab now, put in this path, submit. And I think now this is the experimental bit, because sometimes you get a table, and sometimes you don't. But when it does here, you get a listing very much like we see in TensorBoard. But we can go over to TensorBoard here, and when we do, we get a better experience. We get a nice big TensorBoard area. And here we can start to see all our runs. The mean F1 score is the one we're interested in, and the standard deviation. The rest is not that useful in this mode because we just have one training step. Let's go back here. How's it doing? Still busy. But there's just a couple of a couple of things. Ready? Okay, that's finished. And now we can see, that's fairly tight actually. The hyperparameters haven't done that much difference. And we're getting what sub S score there. It's not actually telling me. The best score up there is maybe about 0.58, something like 582, something like that. Cross-validation score. And like I say, we'd have to go off and compute it against the test set using those scripts in order to be able to compare it to the leaderboard. But that's something we can do. So again, that was just an example of using Ray on a more difficult problem. And then we can go off and try and beat Lucas and Alfredo's result. Okay. So I think, as Lucas said in the channel a little while ago, though, grid search, there must be a better way. And this is one of the things sort of been building up to here, is that we've looked at two things, grid search and random search, but they're only options. They're just two examples of search algorithms. And I'm going to skip over this cluster example for a minute. Well, actually, I won't. Let's do this first. So, let's get this up and running in the cluster whilst we go off and looking at Bayes. Oh no, sorry for the indecision. Let's look at Bayes first. So what we're going to do is I'm going to go back and, sorry about the flipping around here, shut down array. Yeah. Just to answer Lucas's question, the benefit of tuning the table in that dashboard is you just see, you just get a list of the jobs, the parameters that are shown, their status. So I guess it's just an easier view to assimilate, really. But okay, but there must be more than grid search. And this is one of the excellent things about Ray, that now that we've got that pattern established, now that we can launch the clusters, it gives us access to a whole bunch of search algorithms. So in here, we just go to the docs. We've got a bunch of search algorithms available. So grid and random search, but also Bayes optimization, HyperOpt, SIGOP, and Nevergrad, the Facebook AX package, or Bayesian optimization with hyperband scheduling. So all of these things are things that you can just drop in to your training setup. Now you've got the right code in the right shape and benefit from that. So let's have a quick look at the Bayesian. Okay. So the key things here is that when we try and use search algorithms, different search algorithms, yes, we're going to have to, tell Ray to use them, but we have to make some small adjustments to how we define the search space. So let's do that. Let's import the dependencies, including the setup code for SEGI, FSEG. We're going to import a new searcher called the Bayes opt search. We've got our training function, which is the same as previously. I just copied this across. This shows that there's no changes. It's exactly the same training function as earlier. So we don't have to change that piece of code. What we do have to change is the search space. And we have to move away from these built-in tune functions and go with the pattern that the Bayes opt package, which is what's underlying this, actually expects. And the Bayes opt expects a p-bounds object, which brings in a whole bunch of tuples. The parameter names stay the same because our code expects to inject those into scikit-learn. And but then we just have to specify tuples. Now, a lot of these are continuous and can be floating point, but some of these actually need to be not discrete, need to be integer. Yeah, So in order to do that, I've done something here, pass config. I've just written a little wrapper function that will intercept the config before our training thing gets it, our training function gets it, and it'll just round and convert them to integer. Yeah, so that's just the mechanics of that. I guess that's going to affect the Bayes optimization, because the Bayes optimizer is going to be choosing a floating point number, and we're going to be quantizing it. So that maybe does something strange to the optimization, but and maybe somebody has an idea of what that would be, whether it's good or bad or indifferent. I'm not sure. We define a utility function. My understanding of the utility function in Bayes Opt is that's helping us figure out where to draw data from in our search space in order to better optimize the posterior. So that's given us some control over the optimization strategy. And I've just pulled the one out of the docs. And then we set up a search algorithm explicitly. So this is the object we imported earlier. We give it the bounds. We tell it we care about the mean 1f, 1f score, and we're trying to maximize it. And we pass in the utility function. We define a config object for Raytune, and that's just saying here locally we're gonna sample 10 trials. We're going to add this to the config, which was our static random seed, and we're going to do 4 time steps. Okay, and then we just run again. Here's these little wrappers that I put together just to sort out that search space, get our data in. Pardon me. And we just pass the search algorithm into the run function. And that should go off and run. Sorry. Yeah, it's busy. It's off, running. Cool. So there it is, we'll let that run. Me, I've used this a couple of times and I've sort of gone and trusted the results. But one question that sort of occurred to me while I was setting up these notebooks is if this is doing a Bayesian search, how does it predetermine should it be able to predetermine the entire table of hyperparameters then? Or are these things actually updated as it goes on? Because it should be. So that would be a question I have for the Ray guys. That's all terminated. We've got our best config back. We've got a data frame, we've got top head. And we've got the scores back, which is great. So now we've not done branch search anymore, but we've not done random search either. So we haven't just uniformly sampled the random distribution. We've used a search strategy that will apply the Bayesian optimization framework to go off and find the hyperparameters that are best for the job. And it should follow the hyperparameters and spend more time in areas of the parameter space where it's already getting good results. So we should see that we don't get completely uniform distributions. We should see some clumping of our distributions around certain areas. And maybe this isn't, maybe there's a hint of that happening down here and a hint with the estimators, but maybe we just haven't run this with enough samples. So I could go back and run this on my local machine again with a lot more data. But what I think I'm going to try and do is get this up on our cluster and run this notebook with a whole bunch of other trials, and then we can leave it and check in at the end of the session and see what it's doing or how it's done. Okay, so now we're coming back to this other cluster that I had set up. That's in the cluster ray tune YAML file that we looked at earlier. And that has a minimum of 2 workers and up to 8. Okay? Now, like I said, if we were doing this in production, I just want to issue a command and it would go off and do the job and give me the results back. But because I'm not quite set up for that, what we're doing instead is I've got a Jupyter Notebook running on the cluster head node, which is this one here. And we're going to go in, and I've not actually done this yet on this cluster, so let's see if we're in good shape. And let's run this Bayesian optimization now on there with a larger number of samples. So how long did that take on my machine for 3? It took maybe about, 3 seconds and stuff. Should I go for, and we are going to have about an hour before the end of the tutorial, so should we maybe just go for 200? Let's try that. Okay, but I'm getting ahead of myself. We're not quite there yet. In order to do this, we need to modify our ray init call. Okay, so far so good there. But I no longer need to do this. Now, I believe I have to do ray init. And I don't need to tell it what these resources are because it knows. I need to go and tell it to find the address of the cluster, I believe. No, I don't. Ha. Right. I need to be able to get the address. Ha. Here. No, that's the wrong address. Let me step back, because have I already done it in this notebook while I was testing? Aha. Okay. Yes, that's right. Yeah, okay, so sorry for that, flicking about. It's because I had the other notebook set up already, but decided to go this way because there's more interest. Okay. So we're connected to the ray cluster. We have 200 samples. And now we're launching. 200 runs. Pop over here. Okay, one worker's come back up. Okay, well, let's just trust that that's going to go and do something. Hopefully it will scale up more instances, as I think what it's supposed to do. But we're going to come back and check back on that later on anyway. Cool. So we're going to now flip around and do something else. So just in summary, what we've done, we've come along and run this data set now, and we just did the grid search and random search, and we saw there wasn't that much change. But then we went off and strapped in another optimizer, which should give us a much better performance in terms of we should be able to get to a better solution with less searching through using the base opt. And again, that wasn't that big an ask. We defined a few more objects and changed the structure of our search space, and we were able to go off and do that without changing any more code. So that is the sort of real power, I think, of this stuff. Okay, so now for the last part, we're going to flip over into a slightly different world. And I noticed my complete repetitive typo of BHOP instead of BOHP here, but I decided not to rename things and save a push to the repo, but I did spot that. So now we're going to go off and look. I've called this deep trainables. I've called this deep trainables. And why? Because really, Ray at its heart, I think, Ray tunes based around working with deep learning models rather than the sort of models we've been looking at so far. So models that need to be iteratively trained. So far, everything that we've been looking at has used the function interface of Ray, where actually there's another interface available that is A, gives you more control, and B, it gives you access to a bunch of other add-in features, schedulers that Ray give you. And we're going to have a look at some of those now in the context of some PyTorch. Okay. So this notebook is just to take us through the basic pattern with the toy example. So we bring in all the dependencies again, and we have a look at the trainable interface. So it's basically a class. So to build a trainable, you just create a new class instance based on tune trainable, and you override the setup, train, save, and restore functions. Setup is going to do any setup of internal state. It's going to define the network. It's going to set up data loaders. It's going to set up whatever mechanics you need to actually run your optimization problem. Train is going to be our self-contained, idea of our self-contained train val test loop, whether that's a single run of the model and validation against the validation set and computing a score, or whether that's a full CV or nested CV run of multiple models, then that can all go in there. Is that right? No. Backtracking that. This depends how you do it. Okay, let's backtrack on that. I've used trainables in two ways. I've used it in that way where you just set up the model, train, and you train per iteration. And I've also used it to also completely encapsulate cross-validation runs. When you encapsulate the cross-validation runs, you do lose the ability to use schedulers. That's true. However, you can gain the ability to do different things by sticking to that interface. So sorry, that was a moment of confusion there, because I've implemented a couple of different things on trainables. But the pattern we're going to show you today is that the train step should invoke one iteration or epoch of your model. Yeah, and then return training, validation scores, losses, etc. The save function is called for you automatically by Ray, but that's where you should go off and generate a model checkpoint. That should be PTH. Yeah? Sorry. That should be NumPy in this example, but it's usually a model checkpoint. And then restore will actually reload that checkpoint. Now you may be thinking that, okay, this is great. So I can pause and resume my training with array. And it's not quite that. If you're doing hyperparameter tuning, this restore function is to allow schedulers and strategies like population-based training and things like that to auto-load previous jobs and continue from that. So it isn't quite the restore function you're thinking of, but you do need to implement them both if you want to be able to use the schedulers. Okay, so that's fairly simple. So here we've defined one, and this is just a silly trainable that is just, it's just adding whatever's in our hyperparameter config to a variable in the state, returning it, etc. So let's just run it quickly. Boom. It's run. We can see it's done this stuff because it's done a bunch of incrementing numbers, and it's finished. So fine. So that's just the trainable interface, which is the pattern we're going to follow in the rest of the notebooks. Okay, so look at something more interesting. So if you're running this on a machine without a GPU, you can run this on that, no problem. I've included it for that reason. And you can play around with that in here. It's not as intensive as the next example at all. So MNIST is a well-known data set in machine learning. Handwritten character recognition, 70,000 images, split into 60,000 training and 10,000 test. So we're going to just run that classifier here. This is basically one of the Ray examples. And I'm going to click on this link here. Because if you go off in Ray, in the Python, in the GitHub repo, there's a huge array of examples. They've done really well. And but they're all sort of runnable Python scripts, which is great because you probably submit them to the cluster straight away. All I've done is pull that out in a notebook so we can go through it. Okay, so we load the normal dependencies. We're also bringing PyTorch in. We're going to get the data loader from PyTorch. There's another file in the directory, in the file MNIST PyTorch, and that has our data loader function from the examples. It's just going to pull down from the web the data set the first time, and then return two PyTorch data loaders, one train, one test. Okay, we define an extremely simple convnet with one convolutional layer, one fully connected layer. It's currently parameterized by width, which affects the width, the number of channels here. And that's something you could tune over. Train and test functions we set up like before. This is standard sort of PyTorch, where we get a device. We take a model and optimizer and a loader. We're getting our device, which is just going to be CPU. We train our model. We set our model to train mode. We then iterate over our batches. And then we zero our optimizer, do a forward pass of our model, compute our losses, and then step the optimizer. Backpropagate and step the optimizer. Our test function is pretty similar, except that we switch gradients off on torch. We set the model to eval. And here, we're iterating over the batches, doing forward passes of the models, and then actually getting our predictions and calculating the metric. Okay. CUDA is available for me. but I'll leave it on CPU so you can see what it's like with CPU. Okay. We start up array. And now we have a trainable. So this train MNIST, what's it doing? Again, it's checking for the device in here. It's getting our data loaders, because again, we want this to sort of be end to end, and we want it to fetch our data for each worker. We set up our FossilNET, and we could, pass parameters in here if we wanted to tune the network internals like that width parameter. That's something you can play around with later, maybe. And then we set up our optimizer. And here, we're actually getting our learning rate and momentum from the config that is being passed in by Ray. And then the save and restore checkpoints are as per normal. Did I run that? Did we run that? Cool. And now we go off and we tune as before. It doesn't need a GPU. So there's our learning rate momentum, tune uniform for both. I think everything else here is just the same. And we go off, and I've only selected 3 samples, but you can try more if you like. Train is not defined. Yes, I'm going to, because I've not run the cell. Sorry, I should have cleared the notebook and run it completely. Still not, okay. That's what I'm going to do. So I'm actually just going to do restart and run all. Okay. Okay. And now it's off. Cool. And now, while it's doing that, I want to go back up to dashboard, which is started on yet another port. I wonder if I'm closing RAID on. Okay, and then we go off and see it's training, it's only using 1 worker. Let's go off and see why it's doing that, actually. So I've said, because I've said there's only 2 GPUs available. There's 2 CPUs available. And down here, I've told it needs 2 CPUs. So it can only use 1. So let me stop this. Stop that. Stop the training. I'm going to go back up and adjust this to 10. I'm going to go back and I'm going to run the cell again now. And now, hopefully, it should be able to launch parallel jobs. Yeah, that is. There's 3 training mounts going there using CPU. So this is iterative now. So if I go back, let's have a look at TensorBoard. If I go back to here, get that path, put it in here, I think MNIST Trainable. Not a valid directory. Array results. Torch MNIST, train MNIST. Okay, still no table. Enable TensorBoard. Okay. Now, what's a bit strange is I expected to see training curves there, and I don't see any training curves. So let's go back and figure out why that's happening. It should be training up to 100 iterations. It should be checkpointing. I'm just going to pause this one here. That's still running. Okay. So yeah, I'm a little confused as why we don't have training curves here. We only seem to have one iteration, where previously, where here we're telling it to go to 100 iterations. So what I am going to do is I'm just going to try that again. I'm going to delete this folder in case there were previous results or something in there, failed runs. I'm going to have a look in here, and you can see, look, iter. We have training iterations going up, so it's definitely training, but it doesn't seem to have logged at the tensor board. So I'm just going to have another go at that. If I run that again. It's definitely training and iterating. Okay, we're going to get off there, go in, train MNIST. Yeah, it's generating TensorBoard results. So let's reset this, tune. Let's go back, try it again. It's the last try before I flick to one. No, okay. So I have to say that this does show up as a proper training parameters. I just don't know why it doesn't. We should see curves there. That's the last thing we're going to try. Where's I on the right instance of that thing? So the last attempt. Tune, train MNIST, submit. Oh, we have the table. This looks better. Yeah, so like I say, the table is just what we see in Jupyter. We still don't have any training curves, which I'm just going to accept and move on and figure out how to do that later. In fact, it seems to be pointing completely to the wrong results directory, because this is all random forests, and I am not training a random forest for sure. But I'm just going to take that as a demo day bug. And let's go off. And let's just try one of these models at random. I don't know which one was best. Let's get the latest checkpoint. So what I actually want is rename. I'm going to copy this really complicated name here. And then let's just load the model. So we're going to load some, get our data loaders and get some test data. Now from the test data set. Remember all this training, yes, and then from the test data set. And I'm going to put that path in there. So hopefully this exists. So I can do a print path exists, checkpoint path. True, good, the file's there. And it's loaded and predict. And displays some output. And it's not done badly, I don't think. That TensorBoard thing's annoying, but I'm not sure why that's not showing up. But there it is, it's not done bad. See if yeah, 8 and 3, it missed that one. Cool, so anyway, that's MNIST. And I'm going to do array.shutdown. Cool. Right, so MNIST, that's a good little example you can play around with even if you don't have a GPU. So now for something a bit more interesting and a bit of a harder problem. So this is FossilNET. So FossilNET is something that Matt Hall's put together recently. It's available under CC0 license. He's got 3,000 128 by 128 color images across 10 classes. And the full data set is available for experimentation. I think Matt will be publishing that properly soon, but we've got some of the data loaded into this repo. In this tutorial here, we're going to target just 4 classes. The dinosaurs, complete with museum stands for some of them. Fishes, fishes, forearms, which I guess are, what are forearms? I'm not so sure. Is that what, fossilized pollen? Something? And trilobites. And we want to try and discriminate against those, between those. So we're going to load some dependencies. We're going to load some, we're going to set up a data loader. Now this data loader function is quite long. Basically, what happened was FossilNet's also already organized into train val test folders. Immediately, you sort of want to maybe think about doing some CV strategy on that while you're tuning. But I've just gone with the train val test split. We just need to remember that we'd probably want to try better than that if we're trying to do this for real. So long and short, we've defined a data loader function. That is going to return me, let's scroll down, sorry, a train loader and a val loader in order to run our models on. Now, here, it's color images. So questions immediately come to mind. Should we be processing color or should we be making this a grayscale problem? So what I've actually done is I've included that as a hyperparameter. So we're using the torch vision tools here that allow us to basically define a data set as an image folder, and we can inject transformers. So we're injecting some transformers we need, like convert to tensor, but optionally we'll also convert to grayscale, and optionally we'll also augment the data set by randomly flipping horizontally and vertically. And we'll inject those into our train data set in the loader. Then over validation time in the validation data set, we'll apply that grayscale if we need to, but we don't do any of the flipping. That's basically what our test loader is. So the neural network itself, we're going to use Torch Vision's pre-trained models, and we're going to download ResNet. ResNet is not a very big neural network, or the 18 isn't anyway. You've got maybe what there, 10, 12 layers or something. mostly convolutionals, and then an adaptive average pooling, followed by the fully connected layer. And what we're doing is we're going to retrain the fully connected layer. Okay, so I've just written a little wrapper around that, which will pull in the weights. It'll tell PyTorch not to optimize any of the model weights, but then we go ahead and replace the fully connected layer with a fresh initialized layer, which will have requires grad true, so that will be updated. And then we go off and we do just the same as we did before. We've got a train function, nothing new there. We've got a validate function, same as we saw on MNIST. And then we create our trainable class. So our trainable class here is a little bit more involved. When we set up our loaders, we've got to go and get the data. And there's an error in this path, but that's right. So we're picking up the path from my local repo. We're getting the for class problem. And we're also sending in now to the data loaders the batch size, augment, flip, and use grayscale values from the configuration. We initialize FossilNET with 4 outputs. We use Adam, and we're going to also keep track of the best train F1 scores here in the model. Then when we train, we just train, we validate, keep track of best scores, and we return a bunch of metrics. Save and restore functions are as before. We have CUDA available. I'm just saying it's 3 CPUs and 1 GPU available on this machine. Cool. Now open the dashboard. And then here we come to the tuning setup. Now I've noticed there's a potential bug in Array for TensorBoard login at the moment from tune choice. So there's a bit of extra code here to work around that and to get these to show up on TensorBoard. Otherwise, it's exactly the same. We're using a uniform, a log uniform, and some discrete choices to iterate over. Our trainable is the same as before, and we're going to stop when our train score hits 95 or after 200 iterations. Smoke test is true at the moment, so it's only going to do 1 iteration. I'm going to put smoke test on false because I just want to run this. And it's secret runs. And it doesn't. Test data set is not defined. So I'm going to go all the way to the top and spot the refactoring error. Rerun that cell, scroll all the way to the bottom. Stop. Actually, I'm just going to restart clear output. And just do that. Then I know that everything's been run. Cool, it's off. I can hear my machine being a little bit more noisy. One's running. Cool. I may not let this run too long because I can hear my machine. Let's go here and let's see if this thing works. Right, I think I'm learning now that that might not be the right dashboard. So let's go here. tensor board. It's still pointed at these random forest classifiers. So I think the ray dashboard is completely confused. Completely. So let's just make sure this thing is training there. I'm going to go to ray results. I'm going to go to torch FossilNET. The fossil trainable. And oh, sorry. I realize that's going to be a bit small for you. That's better. Cool. Right, with a bunch of results in there, probably from multiple runs, but let's run it anyway. Log the my dog. Yeah, Conda activate T20 fri-ray. Do I have more tensors running on my machine? Sure. Sorry. I've also been working on a Mac for 3 weeks, so I'm using totally the wrong keyboard shortcuts. Bear with me a second. No, okay. So, it's because I quit the process. I'm used to launching things with set sid. Silly. Right now, Toggle around. Now we have some training curves going. Good. Cool. So these are the ones we're interested in down here. And these are different hyperparameter training runs. Here's the train, and there's the validation. So let's pop this one open. And now this is running at the moment. So I think I've got some earlier runs in here as well, because my machine with one GPU definitely isn't that fast. So here's a partial one that's probably coming through now. But basically, this is the type of output that you'll get. We've training for our full 200 epochs, and then sometime along here, we will get the best training result. All of these managed to get up quite early. Down here, we have a blue one, and that one takes a bit longer to train up and doesn't get that far. But some of the models train up quite quickly. And of course, we can see that our best score is quite early on in one of these models, where we're getting up to the 0.72 F1 score. So that's pretty good. We can go into H params and see all those. And actually, instead of me just playing around with those, if you go into the notebook, I have TensorBoard running in the cloud with the results of not this run, but another run I did a few days ago. And I'm going to paste those into the Slack. And you can go No, that's the wrong channel. You can go have a look at the results for yourself. Everybody should be able to access that. What I'm going to do is I'm going to kill this notebook because we've seen this seen it run, as it were, and it's really stressing out my machine running that in Zoom. But then you can go in, follow that link I just posted in Slack. You can go in, you'll be able to have a look at these FossilNet results. You'll be able to go to the H-params module, switch off some of these metrics that you're not interested in. Maybe even the best ones, we're not really interested. Oh, yeah, we are, actually. That was the whole point. Put the best ones up, parallel coordinates view, and now we can see where the best scores came from. So a higher learning rate with low weight decay, smaller batch size, augmentation off and grayscale. No. Grayscale on, but augmentation off led to that one. Interesting. So it looks like grayscale is definitely a factor in the higher models, but augmentation isn't necessarily. Anyway, that's up there. Have a play around. What I want to do next is just come back. We can predict on FossilNet, which I believe I have. I'll not run this, but there's a script here so that once you've trained the model, you can come back and predict. This doesn't use Ray, so I'll spend too much time on it. But basically, we load up the same model. We load up. We point to the right directory for your machine. We load up a data loader pointed at the test folder this time. Remember, we did a hyperparameter tuning on train and val, so we're now testing on test. And then what we do is we can load the model, run the forward pass, and then we see this is what actually happens. And I've got this red, I should have a grayscale, but if we go to confusion matrix, we see that really it gets confused about the fish. It thinks the fish are dinosaurs or trilobites. It's not really convinced of fishes at all. But then the other classes are pretty good. It does well on forearms and trilobites. Sorry, I'm reading it the wrong way around. Dinos get confused between dinos and fishes. No fish is predicted at all. Okay. Anyway, there's the scripts. You can run those and play around with that if you like. So the last thing I'd like to show before we wind things up is the scalability of this with GPUs. So it's completely transparent. Sorry, there's actually two things I want to show. The first of which is the scalability of the GPUs. So it's actually completely transparent. And we'll just do that quickly. So during the break, I just started up an instance on AWS here. And I'm going to SH onto that. Yes. Cool. If I do NVIDIA SMI here, I'm going to have to switch profile back to small. Here we go. You can see we've got 16 GPUs available on this machine, and we want to use those to run FossilNet. So I have my source code already up here. So I'm going to CD to transform, run Jupyter notebook. I'm going to do that with a set sieve. So that should come up, hopefully. It does. Phew. I can just do that now. It sets it out the way. I'm going to go back here. I'm going to go to my Ray results folder. I was sitting there for a minute. Okay. So, in deep trainables, what have we got? Predict on FossilNET, Trainable FossilNET. So this is the one we just ran. So let's run that again. But let's make a couple of changes to the output. We're just going to load our dependencies. Are we? Apologies. Stop. Close. Anybody can see the obvious mistake? Now I need to repeat this. I did not activate my conda environment. So let's just kill Jupyter. Right. Now let's do conda activate. I know this will be difficult to see, sorry, but conda activate T20 fri-ray. Right. Now get Jupyter up. Now do that. Okay, let's try that again. I started in the wrong folder. Oh, I can tell I'm getting tired. Kill. 3, 2, 1. We're almost done now. I go back into this folder. See, slow down. Transfer. Okay. Now refresh. Lovely. Yes, it's better when it goes slow. Yeah. Now if I run that, my dependencies load. Good. So let's just go through this, load this again. And I need to pay attention to this path. I don't have a dev directory, and it's not work in progress. So that should work. And CUDA should be available, for sure. Okay, and now we're set up here. So now there's 64 CPUs on here and 16 GPUs. So I'm going to tell it that it can use up to 60 CPUs and all 16 GPUs. Cool. I'm not going to bother with a dashboard. I'm going to come down here. Yeah, that's right. And I should have run that with sexed, never mind. And then I'm going to run now. Here, it's configured for 1 GPU. Yeah. So let's just get that running. Hopefully it does. It didn't. Test data set not defined. Okay. It's that same refactoring error. run that. Right. Let's just run this again. Oh. Wow. I'm sure I did that. Okay, that's clear output. Okay. Validate is it. Restarted. Okay, it's off running. I've just realized I only set 10 off. Maybe I should have set more. Anyway, let me just go in, SSH in on another terminal. Ubuntu at paste. Lovely. And let's do NVIDIA SMI. Huh. And it's not running on the GPU. Let me figure out why. I took the smoke test off. The smoke test was on, actually. We've got resources per child, 3 CPUs and 1 GPU, please. We have 16 GPUs available. CUDA is available. And our trainable, we set CUDA to be alive. We're going to have one more try at this with the smoke test off, just in case that was it. So you're saying using 1 of 16 GPUs, using 10 of 16 GPUs, but NVIDIA SMI isn't showing it up. Maybe it's too fast. So smoke test is now off. We're going to do 200 iterations instead of 1. Let's try that. So 30 more trials are shown, pending. Okay. I think maybe they were coming in and out of memory too fast. So there we go. Now we've got a model training on all 16 CPUs in parallel with no changes at all to the training code. And that's the important point. As far as our training code is concerned, that process can only see one device. So if we write PyTorch training code that goes off and queries how many devices, please, it'll only ever return 1. So Ray is controlling the amount of resources that that can see, and your code just needs to operate as though it would on one GPU. Yet you can go out and scale that very easily with no code change, and that is an amazing capability for just following the Ray pattern in the first place. Cool. So I'm going to leave that off training, and for a while I'll have a look at the results later. There's a couple more things I want to do before we wind up. I realize we're getting close to time, but I think another 10 minutes will be done. The other thing I want to talk about quickly is, you remember those TensorBoard results we looked at? Now, the thing is about these is we wasted a lot of time in order to, we kept a high number of iterations. Why? In order to allow slow learners to maybe, they might outperform a faster learner to get to where it wants, to give it a chance to train. So, for example, lower learning rates, it might take this curve might flatten out a bit. 200 was probably a bit over the top, but the whole point is that a lot of this time was wasted. The model had already achieved a high score and was stable around there. So what RayTune gives us access to is a set of schedulers that allow us to get away from that. And one of them, which is well known, is called asynchronous hyperband. And what asynchronous hyperband will do is it will aggressively prune low-performing trials early on. So it'll fire off all trials on resources, and it'll monitor them. And then the better-performing jobs will be favored, and it'll prune out the lower-performing jobs, and then fire off new jobs based on that. I'm not going to spend a lot of time on this, other than just to say it's extremely simple, again, to add this. In order to put hyperband on our MNIST example, all we do is import the right ray object from the schedulers module. We do some setup to tell it we want to track a metric, we're maximizing a maximum 100 iterations, etc. And then we pass that in as a scheduler in place of our struct criteria. And then we have hyperband. We'll be able to see this by, if we come down here, at the end where we've done all of our training, we can see that we've no longer 100 iterations on everything. Some things have been terminated very early because they weren't going anywhere. So you can go off and read about hyperband, but again, for Ray, it's one of these drop-in schedulers that you can use. The last example, which I have to admit, I don't have, sorry, just a second. I don't have fully working, is Bayesian optimization with hyperband. So what that does is it combines the Bayesian optimization that we saw earlier for searching the search space with this scheduling ability that will cull jobs early that aren't performing. And that means you've fully optimized that search pattern. You're making the best use of your resources, and you're targeting your search parameter trials into areas where you're getting good performance. This is 95% working, and I intend to fix it. But I haven't been able to pull it together in time for the demo. This actually trains at the moment, but we get the same sort of TensorBoard quirk where I only see 2 iterations showing up. And I'm not sure where the bug is, either here or somehow I haven't specified something there, but I will fix that and push that to the repo once I figure it out. But for the moment, it's just good to see that yet again, to get BOHP up and running, it is a bit more intensive, but not that much really. Again, your code doesn't change. What changes is the search space configuration. We need to use some different objects. We need to drop in hyperband or special version of it as before. And we need to drop in our Bayesian search or a special version of it. And then we just run that, and Ray takes care of the rest. Sorry again. Okay, cool. So that is that in terms of demo. The last thing I wanted to check back on was, remember we said that cluster job runner on the SegWi Facies. I think it finished. So we can plot some results up for that maybe. We have a new winning config. And have we really pushed it any further? No, we haven't. I don't think we have. So that was pretty much sitting where things were before. But what will be interesting is to maybe look at some of these distribution plots to see where Bayes-Opt has been focusing. And I don't know, I haven't used Bayesian optimization much. Maybe people who have can comment about this in the channel later and we can chat. But I was expecting this to, well, maybe this is the thing. Maybe this is that there's not much give in these hyperparameters on this problem. But I was expecting Bayesian, I was expecting this to be more lumpy. It's definitely not uniform. There's a lumpiness to it. But I guess I was expecting it to be more lumpy. Anyway, interested in some discussion on that later. Let me wind things up. I've just got a few slides to close things out. So, I mean, what was Ray? I think we've sort of answered that question in some way that it's a distributed computation framework under the hood. So if you've got any custom framework, you can go custom task to distribute. You can go off and use that low-level interface and very quickly be out working on a cluster, or even just doing multi-process stuff in a maybe convenient way. But on the other side, it is sort of infrastructure on a stick, and it can be frustrating sometimes when you set out to build something and you end up going down a path where you end up rolling a lot of this code on your own. And I think now we're at a point where frameworks like this mean that if you just take the time to look at how you properly adopt something like the sklearn pipelines or a pipelined approach to organizing your code, combining that with the patterns that a framework like Ray wants and going with one of these patterns, then you can easily see with quite little work compared to sort of trying to doing this on your own, you can bring up some serious infrastructure with state-of-the-art capabilities in terms of hyperparameter tuning. So that's the way to go, for sure. Ray has just been, well, Berkeley's just spun out this AnyScale. They've started to do some presentations. There's a good PyData one recently. They're also active on Slack. They have a Slack channel with some support there, some great people on there. And they've started doing their own webinars. So there's an interesting one coming up in a couple of weeks, next week, on this exact topic. So the road to AutoML. Yeah, there's a title. So I think it's a good. I think we're at the start of the Ray becoming really V1 production, and it's exciting time to start using it. Let's have a quick look at this, because I didn't manage to touch on any of this at all, but some of the stuff that they have here is phenomenal. So we have Ray, and then we have Ray Tune, which we've looked at a lot. We've also got, which is actually more mature than Ray Tune, or at least as RLlib, which is a library for scalable reinforcement learning. And when you start digging into this part of the package, they have a huge amount already implemented in terms of algorithms, in terms of different models, things like policy networks, actor critic. Well, they need to RL approaches, I know. But I see those in there immediately. But they've got a huge amount already implemented for you off the shelf. I think it integrates with the OpenAI Gym, as well as other things. And this is a serious RL environment ready to go. What's really good is if you want to play about a bit more, if you go to look at the general Ray tutorials, I put the same link twice. Just a second. If we go up to the general Ray tutorials, then yeah, you've got some RL examples in here. Learning to play Pong, the actor critic network, and you can imagine how this fits well with Ray, with having these actors working out on the cluster. But there's some really good examples out there. And if you're interested in RL, I would start here for RL, to be honest. Ray SGD is something I was hoping to demonstrate, but I haven't had the time to put that together. But basically what they're doing is PyTorch, TensorFlow, they're getting their own distributed training stuff set up. Ray is sort of wrapping that and giving you access to that, but also via the Ray framework. So that what that means is what I hope it means. I've yet to set one of these up. Is that we'll be able to take a large training job, which is too big for GPU, and for Ray to help us do the distribution, not across just multiple GPUs, but across multiple nodes of multiple GPUs, for there to be, and to be a consistent way to actually integrate all those sort of training steps back into the overall SGG optimization. So that one is one to watch. Another extremely useful one. Sorry, somebody keeps phoning me. I never ever get a phone call. No one ever phones me, except for today. Okay. The other thing is Ray Serve. This is quite a, again, recent addition, and it's a scalable model serving. So this gives you what looks like a lightweight set of wrappers to be able to take a PyTorch. Sorry, I don't know where my link is. Yeah, to be able to take a PyTorch model, load it, and then have it served out by the server. What that means is Ray will scale up instances needed in order to respond to the demand on the API, and it provides the API endpoints for you in order to receive image data and set that up. So it'd be nice to have a FossilNET Ray serve up somewhere at some point. That would be good. And something which is really new is the sklearn. And this is definitely still in alpha, but they've started to wrap the sklearn functionality in Tune specifically. And I think that's basically taking it down a level so that we have Tune search, grid search CV, so tighter integration inside of the sklearn patterns and allow that task to be distributed in a different way. So great. So I think that went okay. Nothing blew up, although we had a few quirks over the way. Thank you for joining, and I've enjoyed giving that, and all the code is up there on the repo, will stay there. I hope to make a few improvements, especially get that BOHP working. And I hope it's a useful resource. I hope you enjoyed the tutorial. And happy to have some discussion back in Slack. Thank you.